Our next speech given by Professor Daofei is energy management of hybrid electric vehicle based on linear time varying model predictive control. Professor Li is an associate professor from the Institute of Power, Machinery and Vehicle Engineering, College of Energy Engineering, Zhejiang University. His research interests include intelligent vehicles, vehicle dynamical and control, man-machine environment system engineering, and new energy vehicles. At present, he is the PI of project on intelligent hybrid vehicle domain controller and simulation verification platform. He is a member of ICAVP2021 conference community and secretary of the General Assembly. Okay, let's play the video.
Hello, my name is Jiajie Zhang. Daofei Li is our instructor, and Dongdong Jiang is the third author of the paper. We are from Zhejiang University. Here we are presenting our research on energy management of hybrid electric vehicle based on linear time varying model predictive control. Our presentation is composed of following 5 parts, through which we will deliver a detailed introduction to our submitted research. Here is our research's background. Energy shortages and environmental pollution has attracted great attention around the world. According to a recent report, hybrid electric vehicle is one of the promising short-term solutions, and the global hybrid vehicle market is expected to reach a value of $1,166.65 billion by 2026. Also, automakers in China are pushing for both pure and hybrid electric vehicles under the pressure of relevant policy. For example, new energy vehicle credit regulation. As the core technology of energy development, energy management is to coordinate the engine and motors or generators for optimized fuel economy. Rule-based approaches are still popular in real applications, but it is usually time-consuming. Optimization-based solutions are getting more and more attention from algorithm developers, which have the ability of capturing the entire problem. However, the optimal energy management problem is basically a nonlinear, constraint, and dynamic optimization problem. Existing research are as follows. Dynamic programming or equivalent consumption minimization strategy are well studied. Model predictive control is also widely adopted to solve the nonlinear model, so it usually has the disadvantages of computing load and the difficult handling with nonlinear HEV models. Meanwhile, some studies have also tried to linearize the model and apply the linear time-varying MPC. However, there are limited reports on LTV MPC's implementation for HEV energy management in real vehicles. So, it's of great importance to propose a new LTV MPC algorithm and implement it on real vehicles. As for the HEV, we take an entry-level passenger vehicle with P2 hybrid powertrain for an application example, with basic parameters shown in Table 1. Here shows how we briefly model the target HEV. The engine and motor are modeled with nonlinear functions f and g as equation 1, which is similar to that in our previous publication in reference 7. When modeling the battery, an equivalent circuit model from previous research is adopted, and the equation of SOC can be drawn as 2. As for longitudinal dynamics model, it can be established according to the force analysis as equation 3. For the MPC design, we firstly set the state variable x as V, SOC, and MF, continuous control variable U as T engine and T motor, the disturbance D as FR, and the output Y as V, SOC, and MF. Since the vehicle model have been established, we can obtain a nonlinear model of HEV by combining the above model equations. In order to linearize the model, Taylor expansion is adopted, and we can obtain equation 5, where system matrices are corresponding Jacobian matrix of function f. Besides, the model needs to be discretized in order to be used in real-time controller. Here we assume x tilde equals to x minus x0, u tilde equals to u minus u0, d tilde equals to d minus d0. We can obtain 6 through discretizing, whose corresponding matrix is shown below. For the purpose of obtaining optimal control variable, we rewrite the system equation as 7 by using control increment delta uk with matrices attached to it. We assume the prediction horizon as NP and the control horizon as NC, and set delta u k plus I as 0. Taking the state variable ck as the initial condition, the state 8 in the prediction horizon can be obtained by iterating equation 7. To obtain the optimal control, we define the cost function j as shown in equation 9, including arrow between the actual output and the reference output value, control increment, and control magnitude. For the optimization problem, the following constraints need to be satisfied. For example, T engine has its maximum and minimum value as shown in equation 10. Thus, such optimization problem can be well dealt with through quadratic programming, and the optimal control variable can be obtained to get optimal torque distribution. Before real vehicle experiments, we need to adopt some equipment to realize algorithms real-time running on vehicle, which is shown in figure 1. ETAS bypasses the original algorithm in ETK, so that ETK only receives the control command calculated in micro-auto-box, which runs the LTV MPC algorithm based on feedback vehicle information via adapter. Here, figure 2 shows the scene during the vehicle test. We run the preliminary test without any adjustment to check whether the top-down design process works or not, with results shown in table 2. The vehicle fuel consumption reaches 7.03 liters per 100 kilometers, and carbon dioxide emissions is up to 163.48 grams per kilometer. Both the fuel economy and emission performances are far from acceptable, indicating that proposed MPC in section 3 is not satisfactory. We plot figure 3 and 4 to analyze the reasons of high fuel consumption. According to figures below, there are certain differences between the target and actual torques, indicating failure in responding vehicle controller's request. Meanwhile, the engine torque varies too much and its maximum torque exceeds 115 Nm, such as point A. Besides, the engine starts and stops 17 times under the whole cycle conditions. To summarize, we speculated the following reasons. First, frequent start and stop of the engine, such as interval B. Second, the engine torque fluctuates up and down, such as interval C. Third, the peak of the engine torque is too high. Accordingly, improvements are adopted. First, we set the engine to keep off when the vehicle speed is lower than 16 km per hour, and the engine needs to be kept on for at least 30 seconds after starting. Second, the weight of the engine torque increment is increased. The improved algorithm is further examined in a second round drum test, with the results shown in table 3. The vehicle fuel consumption was 6.41 liters per 100 kilometers, which has already been 8.8% smaller than that in the preliminary test. However, the pollutant emissions deteriorated to a certain extent, except for carbon dioxide. Following figures are comparison and analysis of the two test results. It can be seen that the engine has fewer start-stops and smaller torque fluctuations, which greatly improves the fuel economy. However, there is still a problem of excessive torque when the engine is being started, such as point D and E. So, we further limit the engine starting torque and restrict the torque fluctuations of the engine. In our last real vehicle test, the vehicle fuel consumption is now 6.2 liters per 100 kilometers, which is a reduction of 3.3% compared to the second run test. Carbon dioxide emission is reduced to 144.49 grams per kilometer, and NOx is also reduced to 0.018 grams per kilometer. Figure 8 presents corresponding battery SOC curves. Though the initial SOC of 3 experiments are different, the changes of SOC are very small. To summarize, by applying our proposed LTV-MPC, vehicle fuel economy has been reduced to 6.2 liters per 100 kilometers after only 3 run tests, and varying degrees of reduction of main emissions can be seen from the comparison in Figure 7. To conclude, we propose an LTV-MPC-based energy management algorithm for a P2 HEV. We carry out multiple real vehicle experiments on a dynamometer to prove the feasibility of LTV-MPC. LTV-MPC can realize real-time running on real vehicle experiments. Besides, it can reduce the fuel consumption from 7.05 liters per 100 kilometers to 6.2 liters per 100 kilometers within only 3 experiments. Furthermore, main pollutant emissions can be obviously reduced through LTV-MPC. The efficient process of performance improvements by combining the expert rules shows that the optimization framework of LTV-MPC can guarantee straightforward and effective development of HEV energy management algorithm. More promising performances of the LTV-MPC framework can be expected through detailed modeling or lower-level control, for example, transmission gel ratio. Here, we thank 文钢琴、宁流、玉娇城、雷里, etc. for their help in real vehicle application and dynamometer tests. That's all. Thank you for watching.
Okay.
Hello, my name is Jiajie Zhang. Daofei Li is our.
Okay. Many thanks for Professor Li for presenting their work in developing real-time linear time varying MPC-based EMS for HEV. Thank you, Professor Li.